So we've created a model of population growth, of a simple one, but still a model of population growth, in which we say the population size at some time in the future is equal to the initial population size times e to the kt. Alright, so this is the equation we're going to use. And let's imagine we've got a situation where we're dealing with an endangered species. Okay, the first year of the study, the initial year, we go out and sample, and there are 10,000 individuals of this potentially endangered species. The second year we go out, we find only 8,000 individuals. And we feel like this is a pretty good census, and it represents a decline in the population. Now the question is, what is K equal to if this is true? Well, we know that the new population size in 1 year is 8,000. The initial population size was 10,000. E to the K, there's been 1 year like this, so we can move the 10,000 over, divide both sides by 10,000, we get 0.8 is equal to EK. Exponentiate both sides, and we get, not exponentiate, we take the log of both sides, we got an inverse of E, so we get log of 0.8 equals log of e to the k is simply k, inverse function working it for us there. And that solved for k, so now we can go back and we've got a now model that says y of 0 e to the log 0.8 t is equal to yt in the future. Okay? So now, we could ask a variety of questions. For instance, we could simply plug in 8 here for t, solve this equation, plugging in 10,000 for the initial, and it would tell us, well, what would we have for population size in 8 years, 5 years, depending on what we plugged in for t. We can do something else that's kind of interesting. We can say, well, because of population genetics and loss of genetic diversity, we really don't want this population to fall to 1,000. And so we're going to try to do some things to stop the population decline. But how much time do we have at this rate of decline, k is equal to the log of 0.8, how much time do we have before we're going to reach 1,000? Well, we can do that and just say 1,000, because that's our critical point, is equal to 10,000, the initial population size, times e log of 0.8 t. Okay, we bring the 10,000 over and we get 0.1 is equal to e log 0.8 t. Take the natural log of both sides, we get log of 0.1 is equal to log 0.8 t. Divide both sides by the log of 0.8, we get log of 0.1 divided by the log of 0.8 is equal to t. If you plug in on your calculator, you'll find that that's about 10.32 years, or whatever time frame our model is in. And that would be saying that we have about 10 years before we go from 10,000 to 1,000 individuals. So we better get a move on here and save this species. That's an example how you could use this model derived from differential equations to make predictions in biology. I will note one thing. If this was actually being developed by a biologist, and this is a small point, but they would not use the variable name k. It's invariably written as a small r, lowercase r. And this is called the intrinsic rate of population growth. Same as k, really, it's just a different notation. So when you see e to the rt in population biology, this is the rate of population growth.